We are building a Christmas Ornament digital display for Professor Wayne of the Department of Boston University. This is Matt Larson, looking out of the Sino, and I'm Matt Trunkman. So the motivation and the problem in our project is to modernize our customers' family tradition of having family photographs hung from the Christmas tree as ornaments. And we are doing this by implementing a digital picture frame in the shape of a Christmas ornament. The functional specifications we had in mind when designing this product, as you can see here, obviously it's an ornament being hung from a tree. The device will be able to cycle through pictures in a slideshow format. The device will have USB connectivity. The device will have a battery life of at least 3 hours and display images at a resolution of portability, which is 220 by 240 pixels. The screen for the device will have a brightness of 200 nits, which is comparable to the higher level cell phones of today. The device shall operate at room temperature, and the device will be able to operate through modes that include reverse playback and different graphical transition effects. And the device will go pictures using an input output. So here is the system block diagram that realizes the problem. The focal point of this system is the single board computer in the ornament itself, which runs embedded Linux and has the photographs that will be displayed in the slideshow in the flash memory on the device. There are 2 points in which the user interacts with the device. One is at the user's own personal computer, where they prepare the pictures for upload onto the device, and also on the device itself with the button interface to control the modes of operation during the slideshow. There is the display of our device is a silicon TFT color LCD display, 3.5-inch diagonal, and as mentioned earlier, quarter VGA. And the device is powered via a rechargeable polymer lithium-ion battery, which has a charging circuit and also a low battery indicator circuit. And this is the final product itself. As you can see, at the top is our display with the USB connectivity in the bottom right-hand corner. Here you can see the user interface of the device with the power button, the low battery indicator LED, and the buttons which control the slideshow operations. At the top there, you can see the input to charge the battery, and here is the hangability. And here is in numerical form the final functionality is delivered. One note here is the battery life. As you can see, we were unable to meet our specifications all the time. The battery life depends on how much the user has interacted with the device during operation, so it can range between 2 to 3 hours. So if you just start it under full charge and let it go in normal playback, it can run for 3 hours, but constant interaction with the buttons, uploading of pictures, drops the battery life to possibly 2 hours.
Alright, so in order to properly compare the pictures for a device and save space on our device, we decided to have the user's PC manipulate the pictures and compare them to the device specifications. So we created an application that would be an executable file that we will package on the CD that comes with our device. And it was a simple C# program that ran in the Visual Studio's environment. The original requirement was we were supposed to handle the sending of the images from our application, but we ran into some complications. So we decided to use an application called Hyperterminal to send our images to deal with the functionality of the device and handle these errors. And there's also just a screenshot. There's a preview function where you can see the images, and it's a simple UI. It's run right off the CD, or you can save it to your disk.
The purpose of the slideshow software is to handle and display the bitmap images stored on the device. The software was written in the C programming language and compiled using the ARM GNU cross compiler. The way it accomplishes displaying an image is by writing pixel data to the frame buffer, which is a representation of the image on the screen in memory. A for loop traverses through all the pixels of each file, sending the data to the frame buffer, where it's displayed on the LCD screen. To cycle multiple images, we decided to use a playlist file, which is opened by the software, and it contains the file paths of each image displayed, as well as a number of images to be displayed. This is enumerated into an array, and by changing the index of the array, we can switch images. So reverse functionalities were implemented by using a conditional statement which checks the state of a variable, and when the button press changes the state of the variable, which causes it to begin cycling in the reverse direction. When the index of the array reaches 0, it's reset to the number of images in the playlist, so it cycles through. And the pause button again is implemented with conditional statements that check the state of a variable, and when pressed, the array index just remains at its current value. And the slideshow transition effects were made by modifying the nested loop that writes the pixel data to the frame buffer. So each time this happens, the image rotates 90 degrees. So doing this several times in succession with the timer has the illusion of having the image rotate for display effects.
The three requirements that I had for the buttons were that the play and pause button will pause the slideshow when it was playing, and then have it resume and press it again. And that pressing the reverse button would cause the slideshow to play back in reverse. And that pressing the effects button would cause it to scroll through various effects. And I implemented this by using three pull-up enabled GPIO pin lines, which were connected to a single pull, single throw switch, and those were connected to ground. And whenever you press the button, it would basically drive the pin to the ground. I implemented this in the software by initializing the variables, initializing the timer, and then it would go into a standby mode where it would wait for the timer interval, where it would check the button state and compare it to the previous state. And if the state was different than the previous state, it would change the flag in the program. And if the state was the same, then it would not change anything. And if the slideshow interval wasn't reached, it would just go back to standby mode. But if either or of those conditions were met, it would draw the pictures again.
So, as mentioned earlier, the requirements of the power supply for this device included 3 hours of operation and rechargeability. The components used to realize these requirements was the single cell charging unit, as you can see in the top picture, polymer lithium-ion battery rated at 3.7 volts and 3,000 milliamp hours, a low battery indicator circuit, a power button for a hard on-off switch, and then a off-the-shelf wall wart transformer delivering 4.5 volts DC to the charging cell. Now, on the left, you see the template schematic used to design the low battery indicator found from discoverservice.com. Now, the focal point of this schematic is a IC from Panasonic, voltage detector IC, MN1380 series. Now, the schematic in this image here is for a trip point at 2.4 volts. Our trip point needed to be somewhere between 3 and 3.2 volts because the device requires a minimum voltage of 3 volts to be on. So there was manipulation done to the resistors that set the charge time of C2 above the schematic to change the trip point to 3.15 volts. And the schematic on the left is the schematic for the single cell charger, which allowed for in-place charging of the device, which is very important. We don't want the customer to be opening the device and having to either remove the load or take out the battery during charging, which it allows for the implementation of just the input from the wall wart transformer to charge the device. And here's our budget for the beta version. Of course, for the alpha version, in order to allow for issues with regard to delivery of certain devices in our product, there was multiple